of those to do consistent measurements of the distances. But most of the distances are less than a few millimetres, or very much less than a millimetre, the distances between those polonium and uranium radiohalos.
You can calculate the velocity of the water?
Oh yeah, sure. Yeah, that's a potential possibility. So these are the implications. Fully formed uranium radiohalos require at least 100 million years worth of radioactive decay at today's rates. Only that much uranium would supply the polonium concentrations needed to form the polonium radiohalos. But as I said before, these isotopes, these atoms decay very rapidly. We've been through those. Radon only decays, has a decay rate of 3.8 days, so it's even shorter lived than polonium-210. So the polonium radiohalos had to form within hours and days. So as I said before, 100 million years worth of uranium decay had to have concurrently occurred as the uranium radiohalos formed. So the uranium decay had to have been grossly accelerated. But here's the next step. The granite has the uranium and the zircon in it earlier on as it's molten at temperatures of 650 up to 730 degrees. It has to survive while the granite cools to below 150 degrees before the water transporting the polonium and the radon can produce the polonium radiohalos. Okay, remember the radon and the polonium has only a short half-life. If the granite cooled slowly over millions of years, all the radon and polonium would have decayed away and there wouldn't be any left by the time, or hardly any left by the time the granite got to below 150 degrees to be left to form the polonium radiohalos. So the implication is the granites had to cool within days as well. And I've developed this further. I'm going to present a paper on this at the conference in Pittsburgh. In fact, this is a diagram from that paper to conceptually visualise what happens. You have the intrusion of the granite at around 700 plus degrees. By the time the rock has cooled, the magma has cooled to below 600 degrees, all the minerals have crystallised, including the zircons with the uranium in them. The first release of the hydrothermal fluids, the hot water, is below 400 degrees, but the radiohalos that form from the transport by the hot water of radon and polonium will only form after the rock gets down to 150 degrees. So if the halos form within days, the granite also had to cool that rapidly, drop that temperature right down. Otherwise, you wouldn't have sufficient radon and polonium left to form the halos. It would all have been washed out of the rock and decayed away. Okay, I wanted to test this idea. Let me just go back to this for a minute. Okay, so if hot water in a granite produces these polonium radiohalos, what would it mean if some rocks, some granites have more polonium radiohalos in it than other granites? What would that mean? What would produce more polonium radiohalos? More zircons and more hot water. So you could argue that the more hot water, the more potential for more polonium radiohalos. Okay, so I thought I'd test this idea. In the Great Smoky Mountains, near the Tennessee-North Carolina border, we have sandstones, sand that's been turned to stone, sandstones. Not all of geology is complicated. And these sandstones have been metamorphosed. Now sandstone has no biotite in it. You will not find any biotite in sandstone. But in sandstone you find zircon crystals. Okay? On the east coast of Australia we have beach sands that are mined for zircon. You get sand with zircon in it. It's radioactive sand. Okay? Now, That means in the zircons you've got a source of uranium, but you also got a source of polonium. When these sandstones were metamorphosed, one of the products that was formed, the sand grains were bonded together with clay. It was a clay cement. When the clay was metamorphosed, the clay was transformed like a caterpillar is transformed in a butterfly. That clay was transformed into biotite. Okay, so we have zircon grains as a source of uranium and polonium, and now we've got biotite in these metamorphosed sandstones. And I thought, now what if there was water associated with a metamorphism? I might actually find polonium radiohalos in the biotites in this metamorphosed sandstone. We know they weren't created sandstones and that. These sandstones have fossils in them in other parts of the country. And so I went through that, and I discovered also in the literature that not only was there biotite in this metamorphosed sandstone, but there were other minerals. In fact, as you went from northwest to southeast, from Gatlinburg to Cherokee, along the highway, you actually went through zones in the metamorphosed sandstones where there were different groups of minerals, metamorphic minerals. And at different places along the highway, there is a boundary where one group of minerals changes into a different group of minerals. And at one particular boundary, labelled with the word staurolite, which is a metamorphic mineral, at that line, that mineral is found in the rock as you go further to the right in that diagram. And why is it in that rock? Because there were slightly higher temperatures and pressures, and there was a mineral reaction. Well, this is what the sandstone looks like. The metamorphosed sandstone. There was my field assistant, Kurt Wise. And this is what the metamorphosed sandstone looked like. And you can see biotite flakes in there. Those greeny ones are biotite flakes. And there was a metamorphic reaction, a mineral reaction at that boundary. And what did we see? The mineral muscovite with the mineral chlorite reacted to produce biotite, staurolite, quartz and